Hello, welcome back to the course on audio signal processing for music applications. This week we are talking about the short time Fourier transform. And one of the fundamental elements of this transform is the analysis window. So in this programming lecture, I want to talk about windows, but from a programming perspective. So let's open a text editor, gedit, in which I typed script that what it does is to get a window, in this case the Hanning window, and then it computes the spectrum of the window. But since I have to do all this zero phase windowing and center things around zero and zero padding, at the end the code is a little bit longer than what it would be desirable. So let's go through the code and talk about the main aspects of it. Well, first we have the packages that we need. We import NumPy, SciPy, and Matplotlib. Then we have the lines that relate to the window. So we defined the window length, in this case 63, and the variable that we keep that is M, capital M. Then we call the function getWindow, which it has two parameters, the name of the window and the size. So the window I chose is the Hanning window, which is the raised cosine function. And then I need the variables that keep the middle of the window information. And it has to handle this even and odd situation, so the middle can be different depending on even and odd side, and so the two sides might have a different number of samples. Okay, then we need to prepare the window for computing the FFT, so to place the window at the 0th location. So what we're going to do is we create a buffer of the size of the FFT we want to compute, in this case 512 samples, and then we place the window around the 0th sample. Okay, so we take the second half of the window and place it at the beginning, and the first half of the window and place it at the end. Then we can compute the spectrum of this buffer. Okay, so we'll compute the buffer using the FFT algorithm, and then we convert the complex spectrum into absolute value and phase. The absolute value, in order to convert it to decibels, which is the way that we like to see the information of the magnitude, we have to make sure that there are no zeros, so that the log of 0 is not there. So we will have to check if the absolute value is below this epsilon value, which is the minimum value we can have in Python. That's why we have these 3 lines of code. And then we compute the angle of the complex values. And then in order to show it better, to display the spectrum, the magnitude and phase spectra, and see it centered in the middle, let's say, of the array, we undo this zero phase windowing thing, so that we place back the data in the middle of the array, so that it's easier to visualize. Okay, let's run it. Okay, so we are in IPython, and with PyLab in it, so we have the Matplotlib package already in it, and we can run the script. Okay, that's it. And now we can start plotting things that we have computed. For example, we can plot the window. Okay, so this is the Hanning window, which is this raised cosine going from 0 to 1, and the 63 samples we have computed. Then we can plot how this window has been placed in the FFT buffer. So we can plot the FFT buffer. Okay, so here the window is centered at 0, so we have the second half from 0 to half of the window, and the first half right before the 512 value of the FFT buffer. Okay, and now we compute the FFT and we can plot the magnitude spectrum resulting from that. Okay, so this is the magnitude spectrum, again centered around 0. So here we have the positive frequency values, and in the second part we have the negative values. So a better way to display that, so it's to move things around and locate the main lobe in the center. So that's how we did, and MX1 has the information in the center. Okay. And if we plot the phase, we can also show the location of the phases. And here what is important, of course, are the phases in the middle. And here we have these 2 pi discontinuities, but basically everything is 0, modulus 2 pi. And it's clear, it's good, because that means that we centered the window around 0, and therefore we have what we call a 0 phase window. Okay, in order to visualize the x-axis better, here I typed some commands to plot it in a way that the axes are better shown. So here what I did was to plot against an x-axis array that has been normalized so that the zero padding does not affect. So we divide by n and multiply by m, so we actually see the samples, let's say, of with respect to the window. And I also have normalized the magnitude so that the maximum is 0 decibels. And I am only plotting the values that go in the x-axis from minus 20 to 20, and the dB values I am plotting from minus 80 to 0. Okay, so now if we run this script with these lines added, well, we are seeing the magnitude spectrum of the Hanning window, but with an x-axis that shows the center around 0 and decibels starting from 0. So now we can check the values we talked about that describe the windows. We mentioned that the main lobe, the width of the main lobe, is an important characteristic of the window. And in here we can see, if we look from on the bottom right side, where our x value is of the cursor, and we can see that this main lobe sort of deep is at -2, and this other one is at 2. So clearly this main lobe at this location, the width is around 4 samples, what we call 4 bins, and this is what we mentioned about the Hanning window. And then also we talked about the side lobe level, the highest side lobe level, and here again we can put the cursor at the highest side lobe level, and it tells me kind of the value that this has, and it's around minus 31 decibels, which is the kind of thing that we mentioned. Okay, so now we can keep changing the window, and for example, we can put instead of the Hanning, we can put the Hamming and compute the same script. And okay, that's a different window. And if we can measure the main lobe width, we see that it also has 4 samples, but now the side lobe level is much lower. So the highest side lobe is around minus 42 decibels, which is the kind of things we mentioned in the theory class. Okay, and if we go to another window, for example, we go to the Blackman window. Blackman window, and we save it and run it. Okay, well, yes, that's what we saw in the theory class, and now the main lobe is wider. It's around 6 beams, and the side lobe level is much lower, around 58 decibels. And then finally, the last window that we also talked about was the Blackman-Harris window. Blackman-Harris window that we can compute. And if we run it, okay. So now, in fact, we are not seeing the side lobes. And this is because the range that we are specifying doesn't even reach where the side lobes is. So let's change the display. And let's change the axis to, instead of having minus 80, let's put at least minus 100, so that when we show it, now we are seeing the side lobes. In fact, the highest side lobe is around minus 92 decibels. And now the main lobe is quite wider, is around 8 beams. Okay, so this is a good way to visualize and try to understand the windows. And so please feel free to play around with that. Now I want to do it, but with a sinusoid. So to analyze a sinusoid that has been windowed. And this is another script. This is much shorter because instead of calling the FFT and worrying about all this centering around 0 and worrying about the zero padding, etc., I call directly the DFT anal function that we have in the SMS tools directory. So now what I do is I specify the directory of the models where I have all the models of the SMS tools, and I import the DFT model file, okay, so that I can call this DFT anal function that receives as input the signal, the window, and the FFT size, and automatically does all the operations that we just showed in the previous script. Okay, so in this script, basically what I do is I get a sine wave with a given frequency. In this case, the frequency is 5,000 hertz. Of course, a sampling rate, 44,100. And I compute 101 samples of a sinusoid, which are basically going to be the same length of the window size I am using. For example, in this case, I'm using the Hanning window, but maybe let's change it and let's use I don't know, for example, the Hamming window. Okay, and now we compute the analysis, and here I also display in a way the output so that I centered everything and talked about hertz. So we are going to display only the positive part, because the DFT anal only computes the positive part of the spectrum, and then I will be displaying it, showing it in hertz. Okay, so let's execute this file, test1. Okay, and this is the sinusoid of what I have analyzed, and this is the shape of the window, in fact. No? So this is proves what we talked about in theory, that when we analyze a sine wave and we multiply it by a given window, in fact what we're seeing in the spectrum is the transform of the window centered at the frequency of the sinusoid, okay, 5,000 hertz, and with the amplitude of the sinusoid. The amplitude in this case was normalized, so it's not here an important thing, but we would also see the amplitude of the sinusoid. And of course, we see the standard characteristics of the window, and here the x-axis is in hertz, so we need to understand the relationship between frequency in hertz and all these other values, the beams that we talked about. And of course, if we change the window and we compute the one we mentioned, the Blackman Harris, Okay, so now we do this computation. Okay, and now we are seeing again the Blackman-Harris window, the magnitude spectrum, but centered at the frequency of the sinusoid. Okay, so that's basically all I wanted to talk about in this lecture. So we have been using some packages from Python, and also, of course, we have been using the SMS tools in order to get the DFT analysis code from that. And that's all. So we have been focusing on one aspect of the short time Fourier transform, which is the analysis window, which is a fundamental element, and unless we understand how windows work, it's going to be very difficult to understand how spectrograms and how the short time Fourier transform and other spectral analysis systems work. So please make sure that you understand the concept of windowing and how it affects when either by itself, when it's we see the spectrum, or when we window a particular signal, and therefore so how we see the spectrum of a particular signal having been windowed in a certain way. So thank you very much, and I hope to see you in next programming class that we will basically put it together with the whole code of the short time Fourier transform, and we will be able to understand the whole implementation of the STFT. So see you then. Bye-bye.